Hi, Griffin. Hi, Philip. Can you guys hear me?
Yeah.
Yes. Sorry, my microphone was muted.
Hi, Nolan.
Hi.
Okay, see, I need to get those assignments. What about the midterm, the project?
Oh, at this point, I'm working out like 1 or 2 bugs. I can get it to you tomorrow.
I mean, yeah, I mean, I'm not kind of trying to rush you, but I do need it, like at least by the end of this week.
Okay, I can do that.
Okay. At least if you can't, just give me what you have, and then when you finish something, then you can update it.
Okay, yeah, I can do that.
Okay.
I'll do that as soon as I get this thing charged again.
Okay. Hi, Dax. Where are the other two?
I'm not sure. I mean, usually you're here by now, so I think you could just mark them absent.
Okay. So let's continue with what we wanted to say, and what I'm going to say today is not included in the exam, but it should help us go faster at the beginning of the next semester, unless you want me to include it, which is not difficult, right? So what about the things we discussed last time? The 3 different sort techniques: bubble sort, insertion, selection, and shell sort. Yeah, okay. Can you see the screen?
Yeah, I can see it.
Okay. So the improvement of shell sort over the insertion sort is that we make long distance jumps initially, right? So we start at maybe somewhere further down, and then we keep moving things up. The initial list would consist of every 13th element maybe. So element number 1, then 14 and 27 and 40. That would be the list of the first sub list, and then it will be 2, 14 like that. And then the second time around, the first iteration is through the larger list, and then the second time reduce it and then do a slightly shorter list, and then keep doing like that. And then finally it's going to be 1. It's a list of 1. So the idea is that you want to make those elements which are at the end but which are small, you want them to jump fast, jump up to the top, the beginning of the list fast. So today let's look at, have you seen quick sort? I'm sure you should have seen quick sort for your AP exam.
I think we might have talked about it, but I don't think we looked at it in depth.
Okay. So, I mean, I'll just briefly overview these few sorts, and then we can come back. Unless, of course, I can let you not be here on Wednesday, if you prefer that, because I think most instructors are not meeting this week. So I'll let you decide what you want to do, right? Whether you want to do this or whether you can, right? So have you seen merge sort before?
Yes, we did merge sort last time.
Right? So that's let's finish that then, right? So essentially, how do you do merge sort? You
Are you asking us how we do it?
yeah, how do you do it?
Did you break the like your set of letters or your set of items into two separate sets, and then you sort those sets with merge sort recursively, and then come back with your two sets already sorted, and then you figure out which one goes, or then you merge them together.
Yes, right. So you have two versions of merge sort. One would be to recursively go from top down. The other would be to sort two elements and start merging them together, right? So we look at both of them and say, yeah, which one is called the top down merge sort and the other is called the bottom up merge sort, right? So recursively what you do is, before let's go to the sort part of it. So this is what the recursive sort would look like. No, right? So you would take the entire list and then so this is the entire list, divide it into two halves, right? So it may not be equal, that's okay. So let's divide it into two halves and then around this here, right? And then take the first half and divide that into two halves. And then take the first half and divide that into two halves, right? So then you sort the first half, finally you sort these two, right? So you start EM. So this is, again, looks like the top down, but it's recursive because you're starting with the entire list and then you're dividing it into two and then you sort them. So if I have to write this out, actually, let me go to a blank slide and write it out. You're going to write this out. So I think let's divide this into two halves. And I think it came out to be where did we, right? The R is where we divide this, right? So we divide this into two halves and that's here. Take this one. So essentially the algorithm is this. So I'll show you the algorithm and then we can say, so divide this into two halves, recursively find out where the middle point is, and then recursively if you return if the middle is less than or equal to the low. That means you have come to a list of one element. If you keep dividing into two, so you're going to divide this into two. So you take the entire list, divide it into two halves, sort the left, sort the first half, sort the right half, and then merge it back. Right? But we haven't sorted this yet because this now needs to be divided into two halves like that. And then, but that cannot be done until we divide this further into two halves. And that cannot be done until we divide this further into two halves like that. Right? So it's kind of recursive, but the way it's going to go is it's going to go along the left path all the way to the end. So you can see how it's being done. It's actually going to go all the way to the end on the left path and then recurse back. It's kind of like a traversal of a tree. So the first is going. This is the first sorting that's going to happen. That's the first sort. Then the second sort. So if I draw this as a tree, let's go back to drawing this as a tree, and let's divide this into a tree like that. So you know that it's going to be divided into a tree like this. So it's going to divide it into two, divide this into two, divide this into two, divide this into two like that. Let's say now we have divided this into a set of little list like this. If you have divided into the list like this, now at the very low level, this is called the leaf level, we have 16 leaves, right? So if I have to order the nodes, I have to list out the order. The first sort is going to be this, right? It's going to be sort. Second one is that. Then where do we go after these two? What's the next sort? What are we going to do
Above
after
them.
those? Pardon?
The one above them.
Here,
Yeah.
right? That's where we will go. Then the fourth would be, we'll have to go down here, but then this is going to be 4, right? And 5 would be there, and 6 would be to merge these two things together. That's going to be 6. And then 7 would be to do that, right? And 8 would come down all the way like this. And then if I draw it right, this is going to be 8. That's going to be 9. This is going to be, that's going to be 10 here. Is messed up, but you can see how it's going to be done, right? So 11 would be there. So can you see this? Right? So the recursively, it's going to be 12, 13, 14, 15. Now it goes on the right half of things. Right? It's going to go on the right half of things, but it's the left first and the right first, right next. So do the left sorting, the right sorting. Right? So this is what the top-down merge sort example would do. It's going to divide it into 2, but divide it, sort the left, sort the right, merge. Sort the left, sort the right, merge. Okay? So although the tree might look like this is how it's done. So it's going to look when you're sorting them. So the first 2 elements that's going to be sorted are once you keep going all the way to the left, along the left path, it's going to sort these 2. Then it's going to sort the other 2 and merge these 2 things together. That's sort that one, sort this one, and merge them. You're there. Now sort this one, sort that one, and merge them to get them the list. So you sort this, you sort the right, and you merge them. Now that you have 2 sorted left and right, you merge these 2 things together to get that. Right? So you would get that list. Now go on the right hand side and then do the same thing. So you're going to sort the left, you're going to sort the right. That's the ET and the AX. And then you sort them, you get 8 ETX. Then you sort the other 2, this and that. You sort MPEL, and then you merge these 2 things together, you get ELMP. Right? So when I say sort, you're not really sorting, you're just merging. There is no sort operation, it's merge operation. But while you're merging the 2 lists, you're merging it such that it's all in a sorted order. Like it's sorting by merging. It's not that when I say sort, that doesn't mean you have to switch to an insertion sort or a selection sort. You just divide the list all the way down to 1 element each and then start merging it back the right way. Right? And then when you get to this, you sort the entire thing together or merge the entire thing together. Right? So it's just a merge. You just have to understand how to merge 2 lists together. 2 unsorted lists, when you merge it, you end up with a sorted list. Right? So that's what merge sort is. So the important thing is that yes, it is going to be a merging operation, not a sorting operation. For example, let's say you have a list that's like this, and you want to merge them together. Let's say how the merging thing works. To merge them together, this is now. Do we need to have another array? Can we do this in place? Can you merge in place?
No, we can't.
You can't, right? Because this is a sort that's not an in-place sort, because you need an extra array. And how big is the extra array, the size of the array?
It would be, well, the size of the size of the first one added to the size of the second.
Yeah, the size of the original array, right? So because the size is going to be the same as the original array, now if the size had been less than log n, then you could call it in place. But the size is n, therefore it's not considered in place merge sort. Right? So yes, every sort requires extra space, but the extra space requirement is less than log n bytes. If the data requires n bytes and the extra space is only log n, we call it in place. But since it requires an auxiliary array, which is entirely the total full array, so we call it a non-in place sort. Right. So the way it's essentially merging. So you take this list and let's copy this into the two different arrays. The auxiliary array. And then we merge the list together. So take the first element on this side and then take the first element on the other side, compare and see which one is the smallest, and the smallest moves up here. Right? So that had been moved up, that's gone. Now so it's kind of like two stacks. Right? Two stacks. Look at the top element on the stack with the top element on the other stack, and whichever that's smaller gets moved into the right position. Right? So now it's E and C. So compare these two things together and you copy this back here. So now it's E versus E. It doesn't matter which one we move. So we can move the third, let's move this E here. Now it's again E versus E. We can move the other E back here. You take the next one, and then we can start off, we'll move this. So it's E versus G, and E comes up. Next time it's G versus R, and G moves up here. The next time, so G is gone. G is not there. Now the next one in the top of the list is M versus R. So M moves up here. Right? Now R versus R. Now there are two R's. So now take R and put it over there. Now once we have moved everything, we can just copy the other two right away. There's no need. If you have exhausted one list, you just move the entire list because each list is sorted. So you're really merging two lists that's already sorted. Right? You're merging two lists. So you break it down into all the way down to one element each. A list that contains one element. So that if you have n elements, the first sorting is going to be n lists of one element, or the low level sorting is going to be n list of one elements. And you end up with n divided by 2, half n list of two elements like that. I mean, every time it's going to be a sorted list. So you are merging list that's already sorted. Right? So for one merge like this, what's the cost of this? And the number of compares.
Would it not just be the size of the final array?
N. Right? It's n. How do you show that it's n?
Well, because it's one compare per each letter that's being added. So
yeah, it's one. So you have a list, yes, right? So you have two sub list, two sub list like that, and you're going to merge that into one big list, and then every compare operation moves one element to the right position. Right? So every compare operation moves one element to the right position. So therefore, there are n elements. There will be n compare operations at most. You can have less, but at most n compare operations. Like for example, this is another technique that people remember. This is called pigeonhole principle, a kind of a pigeonhole principle, meaning if there are n pigeonholes, and then you put all the pigeons in their pigeonholes, and you can find out how many are there. If there are n, and if you can map everything to 1, then you know there are exactly n. If you cannot map everything to into 1, then there are more than that. Like for example, let's say you have 235 teams that's competing on a knockout tournament where two people play against. It's a tennis tournament, right? There are two people play against each other, and then the winner goes to the next round. So on the game, the question is, how many games do you have to play before you find out the number of the winner? How many total number of games do you have to play? So the first level you'll pair, let's make it easy for that is the first round. Let's make it 236. So how many games do you have to play before you get to find out the total number of games you have to play? How many first round games do you have to play?
118.
118. And what about the second round of games you have to play?
59, yeah.
Okay, right? So can you add all of them? Like if there's a bye, then he gets to play in the next round, but not on the same round, right? So can you add all of them and find out how many games would you have to play? Right? Well, that's one way of doing it. The other way is like what you did already. Like there are 236 players. So how many losers should there be? If there is one winner, how many losers do you need?
Oh, 235 in the end.
235. And how many losers do you get per game?
One.
One. Right? So how many games do you have to play?
235.
235. Right? Because each game produces one loser. And to get out of the tournament, you'll have to lose a game. And that means you need to have 235 losers. So therefore, it's 235 games. Right? So this is the similar principle where like exactly like what we did here, right? You're comparing two elements, and each element moves one to the right position. So therefore, you need to have n minus 1 compare operations, which for us is call it n. Okay? So it's n minus 1 compare operations. So therefore, there will be n elements merged together. So what's the total number of compare operations? How many steps?
Is it not 235?
For the game total, yes, it's 235. I'm sorry. I'm back to the merge sort. Right? So what is the total number of compare operations?
N minus 1.
Like the entire thing. For the whole.
Right. Because
what's the number of steps? How many steps are there? How many levels?
Log n.
It's log n.
Log n.
Log n number of
steps. You're doing n compares, so n log n.
N log n, yes. Right? So the total, because if you have 10, because every time you divide it into 2, so the number of steps is going to be log n steps till you get to the single element level. Right? So we'll show that next semester that it is n log n. So this is one way of doing merge sort, and so to do that we just have, so this is the simple, so you have a merge operation and a sort operation. How do we merge the operation? What does the merge operation do? This is the merge operation. You have been given an array, an auxiliary array, the low, the mid, and the high. Right? Those are the inputs to it. what you want is the sorted elements to be back in the original array. Right? So you haven't given an array, and you also given an auxiliary array. You want to do this like that, right? So first thing you want to do is copy all the elements from the original array to the auxiliary array. Now, you could make it a little more efficient by not doing this initial copy. Like, you don't have to copy everything to the auxiliary array and then copy it back. I mean, if you want to be a little faster, you can copy from the original to the auxiliary to the original. You can merge it like that instead of making an initial copy all the way to the other side. Right? So copying from one list to the other is kind of like a waste in a way, but then you have to maintain because the final requirement is that you return the original array. You have to make sure that the finally sorted elements are back in the original array. So because of that, if you want to make it easy on you, just copy all the elements. Copy all the elements into the auxiliary array. All the ones that need to be sorted. Right? Copy all the elements to be auxiliary array. That's just a loop to copy all the AK into the auxiliary of K. That's a simple sort, a copy operation. Right? Then what you're trying to do here is now you're going to do a loop. Initially set the I and the j to the two things. So what if you have an element? So initially this is going to be low, that's going to be mid. So j is going to be there. That's the I, that's the j. Right? So start with that, and then you keep doing that until the elements we reach the high. So if I is less than mid, so yeah, this is to make sure that the reason why we are doing this is because we want to make sure that I has not reached all the way to mid. If I has reached all the way to mid, that means you have already merged the entire first list, right? If I has reached all the way to mid or j has reached all the way to high, you have, so if that happens, all you have to do is just copy these two things. Copy the remainder of the other list into the original list. Right? So this first part is to say if I has reached the mid, that means let's copy all the, you have a list like this. You have a list 1, list 2, and that means you have copied all these elements, and j might be somewhere here. Copy the remaining elements from j into the original array. The other one says if j has reached the high, copy the remaining elements of I into the original array. Right? So that means you have, right? The other case is where you compare these two and says if j, whichever is less, copy it into that and increase the j++. Right? So whichever element happens to be less, you compare j and I, and whichever happens to be less, copy that into the original array and then increase the pointer. Right? So this is what the merge sort is, the merging of the two. Right? So to merge two lists, this is how you would merge them. And the sort itself is pretty straightforward. The sort is a recursive sort. Where is my recursive sort? That one. The sort itself is recursive. All you're trying to do is sort the divide it into two, sort the left, sort the right, merge the list. Recursively. Have you seen the keyword called assert?
I haven't.
There's a keyword. Have you?
No.
No.
So this is a Java keyword. It's actually useful when you're trying to test something. It's all you have to say is, let's say for example you're writing a program that has statements S1, S2, S3, and when you and this is what the statement is going to the program has. The assert statement simply says assert that that condition is true when you reach that point. Right? So you can simply say assert. The statement looks like this. It's a keyword, assert x greater than 0. Right? So if you say assert x greater than 0, that means when the program reaches that point, you want an assertion that that condition is true when the program reaches that point. If that, so it's going to do an additional check, and if that assertion fails, the program is going to fail there. The program will fail with an assertion error, meaning that, okay, you wanted to verify that this condition has been met. That condition that you have specified has been met when you got to that point. Right? So it's kind of like putting a system.out.println line to verify, oh yeah, this is what it is, but this is more like an assertion. We can say, yeah, but I want you to verify that this condition has been met before you go to the next line. That's what an assertion is. Right? So it's a keyword. It's a Java keyword. Right? So you can simply say assertion, say assert that that's true. Right? It is used in the debugging purposes. When you're developing a code, you can put those assertions inside. Right? And the advantage of this, which compared to system.out.println type of statement, is that if you, first of all, you need to know exactly what the value is. But if you know this, you have a way when you compile this, you can enable and disable assertions. Right? So when you enable assertions during compiling, then the assertion statements are compiled. So when you're developing a program and you put all these assertions in the code, everywhere in the code you have the assertions sprinkled all over to verify that those conditions are met as the program reaches runs through the code. You can put assertions all the way in. And then, but when you want to distribute the code, you want to disable all the assertions, because now you don't want those code to be there. You want to catch them more with exceptions, proper exceptions, than with assertions. So you can disable the assertions, and to do that, this is how you would enable and disable assertions. So you can run a program, right, with assertions. This is enable assertions. That means all the assertions statements would be enabled. You can disable assertions. That's the default, and in which case all the assertions would be ignored. All the assertions would be ignored, so that even if there's an error, it's not going to let the other person know that there's an error. You will have to catch it and disable it. Right? So assertion is built into these statements. An assertion is a statement that you write something to make sure that this particular condition has been met when this program reaches this point. And if it has not been met, the program will fail with the assertion error. This is again one of those features which was added later on. So assertion is not a keyword in the original Java. So if you're looking at Java 1 through 1.5, you'll find that assertion could have been used as a variable name. But now you can't use it because assertion is a keyword. Right? So assertion is a technique that you can use. So assertion, Java assert statement throws an exception unless the condition is true. So there are two versions of assertion. One is assert x greater than 0. That means it's failed with an assertion error, saying assertion failed if it had to. The other is an assert statement, x greater than 0, and put a colon and write something here, system.out.println. I'm going to shorten it with system.out.println and then say x equals x. Right? So when the assertion fails, it allows you to identify what the x value was. Right? So if you add this to the other side with a colon, and when you add it to the other side, so it helps you. Like, I know the assertion fails, but wouldn't it be better if I had told you, if you had identified what the value was, whether x was 0 or 10 or 50 or whatever it is, or -1, whichever, whatever it is, right? So this only prints out when the assertion fails. Right? It's kind of like a system that you can use it like a system.out.println to say, okay, the assertion failed, but assertion failed, the x value was that. Right? So that's a keyword that's in Java. And you can disable and enable. Right? So the best practices used to check internal invariants and assume all assertions will be disabled in the production code. Right? When you're going to say, so do not use this for external argument checking, meaning don't use it internally. You check that. It's the internal checking. So this is what a top-down sort, merge sort is. We could do this in what's called a bottom-up merge sort, and the way that works is like that. It's almost very similar, except that the only thing that's different is the way you write the code. Right? So if you have the same code, the same letters to be sorted, in my new assignment, I actually posted this as also an additional question. If you can do this, if you don't have time, you don't have to do that. I posted the new assignment based on the sorting things. They're non-programming assignments. You just have to write the trace of the program, something like this. If I say write the trace, that means you just have to write something out like that, like how the book shows how it's done. So you have to. So this is the bottom-up merge sort of it. You take the two elements, you start merging lists together. Merge this with this. Right? Take one element at a time, merge that with this. So when you merge this together, what do you get? E EM. Right? Merge these two things together.
You get GR.
So you go all the way. The difference is that you go all the way through merging two elements at a time. Right? Now do the same thing all the way through. Take these and merge them together. Right? So it's EM merged with GR. So it's going to be EG. and take it out, go do the same thing. Now merging these lists together. Right? So you get E, G, M, O, R. What happened here? Why did this? There's a G here, right?
Oh yeah, I think that should have been a G.
That. Okay? So that's what the bottom-up version of the merge sort would be. Right? So the code, the only difference is that we can write this. The code, I'll show you the code here. And this is how it's going to be done. If you're going to do a bottom-up merge sort, that's exactly what I showed there. You start with two elements, sort them together, and then you go like that. Merge them together, and then merge them together like that. The code is this. One of the things you would find in this book is that when you get to the next chapter, the code is very, very small, a few lines. He doesn't waste a lot of semicolons and colons trying to explain to us what the thing is. Right? But it's very, very important that it's extremely small and compact and concise. Very nice code. It also shows us how to choose this book because first, of course, it's easy. It's very clearly written, and the code is so good that you can learn from it how he writes his code. I mean, with 5 lines, you have an entire merge sort. Right? And the way you're doing, so what's happening here is that the size becomes, so essentially what happens is the size doubles every time. Right? So the size you were using, initially the size was 1, and this until the size becomes less than n, but every time you're going to double the size. Right? So size becomes size plus that, and then you go through all the way like that. Merge. Right? So this is what this is a non-recursive merge sort. It's not doing a recursive sort. It's non-recursive. So I'll stop with this, and then we'll continue with everything else. Maybe. So what do you want to do next on Wednesday? You want to take it off day off and prepare for your tests? We can do that if that's what the others are missing too. So I don't want to keep doing things and find that I had to repeat them again. Right?
True.
So because I wasn't supposed to teach anything this week. Right? So what I'll do is if you have any questions, if anyone wants to meet with me, please email me. We can meet at the same place. Right? So email me saying, I have this question, I need to talk to you about something. Email me. All right? I'll be available. You just have to let me know that you want me to be here. Right? So, and the exam is only on these sections 1.3, 1.4, 1.5, and 2.1. It will be a 2-hour exam. It will include some code writing and some tracing of the algorithms, analysis of algorithms, like the homework problems we did. It will be very similar to the homework problems.
So would we be meeting again next week then?
We don't
Okay.
have, no, next week, no. This would be the
Next
end
week, no.
until, no.
Okay.
Do you have anything next week? No, right? Next week will be the exam week,
Okay. Yes.
right? So I'll send the exams to your proctors next week. You can schedule the time and then you can do it with, you can schedule it and do it with them.
That's great. And then after that, I don't know how the schedule works. Then we have our Christmas break, but I don't know how it works.
Yeah, we have the Christmas break and then we'll be back, I think, after the 12th,
After the 12th.
right? So, I think we start on the 5th, but we don't have instructions on the 5th through 12th. So I think the first instruction day will be the 12th of January. And I'll post all the schedules again on eCollege. Right?
Okay.
And what I'm hoping to get through by next semester is chapters 3 and 4, as far as I could. Right? Finish up the chapter 2, which is merge sort, quick sort, and then heap sort. And there's something called heap sort, priority heaps. And then let's see how much we can go. At least, if not spend time on the details of the analysis, I'll actually describe the analysis and the code for that. Right? So that technically would cover what you would learn, at least give you an overview of what you would expect at the university, this data structures and algorithms class, which usually is a sophomore class, not a freshman class. So we'll see how much we can go in that. So my aim is not to make you masters of this, because you're going to see all these things again, so that we kind of just to keep us interested in this stuff, just to encourage you to think a little more and try out a few more things. So we don't have to master it, as long as we know it should keep us challenged. That's all it is. So some of these algorithms can be very tricky, and actually the more trickier it is, it's very interesting. This stuff is not that interesting because you have already seen this before, right? And a quick sort, starting from quick sort, it might be new things. So any questions or anything we have done so far? No? So all I need is all your assignments turned in. I'll email you all the things I have. You can check. And then whatever I'm missing, I'll email you. Okay, I'm missing this. Can you send me, upload this? Okay, so then I'll let you go. And then I'll see you back after next year, beginning of, right?
All right.
Thank you.
All right.
You're welcome.
Thank you.
Well,
Thanks so much.
thank
Yep.
you.
I'll see you later.